Hello everyone, and thank you for dropping by my digital poster. My name is Benjamin Hardy, and I'm here to talk to you about noise considerations for a microsolenoid at 15.2 Tesla designed for MR microscopy. At 15.2 Tesla, or a Larmor frequency of 650 MHz, MRM is capable of capturing deep tissue images at very high resolution. This 3D image of an excised mouse brain was acquired in 4 hours and 22 minutes at an isotropic resolution of 20 microns. But what if we want to image at even higher resolution? It is apparent that the time needed for more encoding steps and/or more signal averaging quickly can get out of hand. We can understand this by observing this equation. As the voxel size shrinks, the number of spins in that voxel decrease, shrinking SNR. Methods to reclaim SNR include shrinking the RF coil, as SNR is inversely proportional to the diameter of the coil D. To minimize noise, we can change the temperature of the sample, the coil, and therefore the temperature-dependent resistivity of the circuit. Thus, the hypothesis, by controlling samples, miniaturizing coils, and cooling circuits, SNR can be maximized for MR microscopy. As mentioned before, we are using a Brooker 15.2T magnet with 1 Tesla per meter gradients, a Brooker cryoprobe cooled to 30 Kelvin, and a preamp cooled to 77 Kelvin, a custom-built solenoid setup seen here with a 1.5 mm solenoid, and Molex microcapillaries for very small samples. Relative contributions of the sample are noticeable in coils greater than 1 cm in diameter. We can show this with the cryoprobe even though it's supercooled. As we shrink the sample volume of a potato, the noise drops and the Q factor goes up for each loop in the quadrature-driven coil. For coils below 1 cm like microcoils, sample noise is negligible. We can show this by shrinking the sample within the microcoil and seeing that the SNR stays relatively constant. Thus, most of the noise originates from the circuit or the solenoid. The easiest way to achieve very high resolution and reclaim SNR is by decreasing the coil size. As we shrink the coil size down to 200 microns in the plot on the right, the time it takes to achieve isotropic resolution goes down drastically. We can also demonstrate this by comparing a 1.5 mm solenoid to the Brooker cryoprobe. With the same acquisition in the same sample, the copper and silver solenoid outperform the supercooled Brooker cryoprobe. This relationship is well understood by this plot from an abstract from the 5th International Conference on Magnetic Resonance Microscopy in 1999, where the SNR is inversely proportional to the size of the coil, until the features of the coil reach somewhere around 300 microns. The relationship is shown here for 15.2T on a log-based scale, where the SNR follows the inverse relationship with the coil diameter. With respect to noise from the temperature of the coil, it is difficult to insulate samples from extreme temperatures inside the cryogenic volume coils. However, what if only the tune and match circuit is supercooled and the solenoid and the samples stay at room temperature? To explore this, the quality factor of the circuit on the bench was measured with the S11 scattering parameter. Unloaded at room temperature, the quality factor is 168. After immersing the whole circuit, the curve moves, indicating the loading or impedance of the circuit has changed. After retuning and matching the circuit while still immersed in the liquid nitrogen, the Q factor has increased to 394. Change in SNR follows the root of change in the quality factor, thus the change in SNR for the whole circuit would be roughly 1.5. Next, we only immerse the solenoid, and Q increases only to 325, equating to an SNR increase of a factor of 1.39. Now immersing only the tune and match circuit and unavoidably some of the coax cable, the SNR factor increases to 1.43. In conclusion, the sample noise is negligible for a microcoil less than 1 cm. The SNR was shown to follow the inverse of the diameter for microcoils with diameters 200 microns to 1.7 mm in size, and cooling a circuit to liquid nitrogen temperatures results in a factor of 1.5 increase in SNR. Thanks for listening, and I hope to meet you in London.